Welcome back to Multivariable Calculus. Today we're going to start a new chapter. 2.1 is the vector functions. Um, we've already done vector functions, but we've only done vector functions of lines. But we haven't really touched into a general vector function yet. And we're going to be dealing with all different types of things you can do with vector functions in three-dimensional space in this chapter. And I think I've already said this, I don't particularly like this chapter, but it is in the multivariable calculus sequence, so I'm going to have to teach it. So you should have already been exposed to vector functions in part of your parametric functions parametric functions chapter in Calculus 2, or maybe in one of the chapters in AP Calculus BC, which is called vector valued functions. But it's basically the exact same thing. But a vector vector function is a function of one input that spits out multiple outputs. You're going to have different types of functions that have multiple inputs that spit out one output, but that's next chapter. This chapter, it's one input, and you get multiple outputs out of it, right? Usually a numerical value in x, y, z coordinates of an object. That's actually kind of wrong. It could also be a velocity, like a component of velocity or acceleration. So it doesn't have to be x, y, z coordinate, but it is it does indicate a magnitude and a direction, where the magnitude is simply just the absolute value and the direction is denoted by the vector, like the slope. So we're going to be doing various things with this. First of all, the first thing that we're going to be doing is the limit. So limits act the exact same, and if one limit fails, the entire limit fails. The entire thing does not exist. So for example, well, actually there's no example, it's just this, right? But the limit as t approaches 0 of three functions x of t, y of t, z of t is the limit as t approaches 0 of each of the functions. But if one function fails, it doesn't exist. So try to do this example, and I will come back later. Okay, did you do the example yet? I hope you did. Okay, let's do the example. So limit as t approaches infinity. Now limits at infinity and limits at 0, different things. Usually you might get 0 over 0, but limits to infinity, you can't really get 0 over 0. You will get a different type of discontinuity instead. So you'll get infinity over infinity most of the time. On the top right here on the left, you'll get negative infinity over infinity, but I don't need to do a limits review because you should already know your limits. We're going to do some more limits, but it's not a very important part of this course. So to find the limit of the first one, you got to find a leading coefficient of the highest power term. In this case, it's 1, right? It's t squared over negative t squared, so that is negative 1. Now tan inverse of t goes from, well, arctan, or tan inverse of t, goes from 0 to infinity, but the range is actually negative pi over 2 to pi over 2. So or no, not the range, no, well, yeah, the range, I'm sorry, it is pi over 2. 1 minus e to negative 2t over t. So e grows very fast, but e to negative 2t actually grows very, very slowly down. It decays down pretty slowly, right? And it's eventually, the limit as t approaches infinity, e to negative 2t eventually goes to 0. So 1 minus 0 is 1, and then 1 over infinity is 0. So the limit is 0. So that is what you should get. Now, sketching curves. This is going to be the hardest part of this chapter, right? The derivatives and the integrals, we're going to have that in there as well, but that's going to be easy. This is the hardest part of this chapter because we have to be able to parameterize, and we have to figure out the parameterization to be able to figure out patterns so that we could draw the correct curves. So for example, let's say in 2D plane, I think you've already heard of this. If you have x equals cosine t, if you have x equals cosine t, if you parameterize it like this, x equals cosine t, y equals sine t, this is the duality of the parametric equation and the vector equation. You can transform one of them into the other. You should be familiar with this form. If I put r's in there, you'll probably be even more familiar with it. It's the polar form, and it's the form that produces a circle, right, in the clockwise direction. So this is the curve, and the important thing is also to know the orientation. So you have to know the orientation of where the curve is going to go, and you could do that by there's a technique later on in the chapter, but you should just pick nice points, right? So cosine t, sine t, so what I would pick is t equals 0. That will get you 1, 0. So 1, 0 is just right here. And then pi over 2, which will get you right here. So cosine pi over 2 is 0, sine pi over 2 is 1. So it goes from here to here, to here, to here. So it's a circle, right? Now, this is a pattern that you're going to see a lot in maybe your problems, maybe your test. Cosine t and sine t. If you see cosine t and sine t, or any combination of the two, well, if you see like a cosine t and a sine t, negative or positive in any of the xyz direction, you know there's going to be a circular type motion somewhere. In this case, it's going to be a circular type motion on the xy axis. Now we have this kind of pesky 1 minus cosine squared t right here. So what does this term contribute to the cosine t and the sine t? Well, the cosine t and the sine t means that if you look at it up above, what you will get is this kind of graph. So you'll get something like this, right? But it won't be like that because it'll have bumps on it because it's going up and down the z-axis. And the exact bumps that it will have is actually if we have a graph right here, just right here on the side, if we have a graph of 1 minus cosine squared x, y equals 1 minus cosine squared x, what you're gonna actually get is you're gonna get something like this, right? You're gonna get something like this, right? And this is actually the same thing as cosine t, sine squared t. So you're actually gonna get this exact same graph wrapped around. You're gonna get this graph wrapped around the z-axis, and it's a little bit hard to visualize, and the easier way to visualize it would be just to plot points. So what you end up getting is if you put t is equal to 0, then you will get cosine, well, 1, 0, 1, or yeah, no, t is equal to 0, so 1, 0, 0, so you'll get 1, 0, 0. Let's say that's right here. And then if you plug t is equal to pi over 2, you will get 0, 1, 1. So 0, 1, 1. Let's say that's right here. Okay, that's going to be really hard to draw actually. Say that's right here. And then if you plug in t is equal to pi, you will get negative 1, 0, 0. So you will get something like this. And then you will get something like this. So 0, negative 1, 1. So what you end up is a graph looking kind of like this. And remember when I drew the graph at 0, it was bouncy. So you're going to get a bouncy kind of a bouncy graph like that. Let me draw it again. There you go. That's what it'll look like basically. It'll be bouncing up and down for the z-axis from 0 to 1, and it will still be following the circular motion, so it will still be going, the orientation is like this. So it's a little bit weird, but you'll get used to it. Actually, you probably won't get used to it if you aren't already used to it. This is the second time you've seen it. You should be somewhat used to the circular motion at least, and you can plot points if you don't know how the graph is actually going to look like. Okay, so this is another example, another pattern that you might find is the same thing, right, as line. Well, it's not really the same thing as a line, but you will see it's a constant plus a variable to a power, or like something done to that variable, and you will see the same thing done to that variable for every single like every single part, with nothing extra, every single component with nothing extra except the constant. So what this can be actually be parametrized into is 1 plus t cubed minus 5 plus 2t cubed 4t cubed. How you can rewrite this function is actually r is equal to 1, negative 5, and 4 plus t cubed times 1, not negative, 2, and 4. So this looks awfully similar to an equation that we've already done, which is the equation of a line, right? And in fact, this is the equation of a line. The only difference is with the t cubed. And what does the t cubed contribute? No, it doesn't make the particle go at constant speed through the path. But otherwise, it doesn't really contribute anything else, right? Is basically what I'm trying to say. So let's graph. 1, negative 5. Okay, let's put our XYZ markers. So 1, negative 5, 4 is probably something like, well, like that, and then like that. So that's 1, negative 5, 4. And then t cubed 1, 2, 4. 1, 2, 4 is probably something like 1, 2, and then 4. So it's probably something like this. So the graph will probably look something like this. Okay, that's a very, there you go, something like this. So it'll go something like that. It will go in the upward direction because I used t equals 0, and then, but to get the next point I put t equals 1 in there, so you will get something like this. But it does move faster after t equals 1, and it moves slower here. So we could use more arrows to we could use more arrows to not just say the orientation, but also the speed of how fast it goes. Right, so this is with the t cubed. This functions with the t cubed. What changes when there's a t squared instead of a t cubed? So what actually changes when there's a t squared is t can never be a t, like the coefficient before the vector, the t coefficient, the coefficient of the function before the vector cannot be negative, right? So the t squared cannot be negative is basically what I'm trying to say. So this will get you r is equal to 1, negative 5, and 4 plus t squared times 1, 2, and 4. So you'll get the same function, but there's t squared, and t squared can never be negative. So you will never get something that is, right, you will, like the line will never be negative. Or that's kind of a bad description. The line will never go below t equals 0, or it will never like continue past t equals 0. In fact, what it will do is it will go up. It will go back up. So what line you will end up getting is you will end up getting something like this, right? You will get like this, and then you will get like this, where t equals where t equals negative 1 is actually, wait, no, that's wrong, I'm sorry. So t equals 0 will get you 1, 2, 4. T equals 1 will get you like 2, negative 3, and 8. But t equals negative 1 will also get you 2, negative 3, and 8. So it's actually going both ways. The function's going both ways. It's going down, and then it's slowly going down all the way here, and then it's going back up. That doesn't look like it's differentiable, but it actually is vector differentiable, because it's going down and then smoothly going down before it's going back up. It's a little bit weird to visualize, but 1, negative 5, 4, t squared, 1, 2, 4, this is the vector function that this line's associated with. It's kind of going down, it's going up. It's not going the other way because we're not having anything depend on, like any of the y, z, or x depend on each other. Instead, it's depending on one of the variables itself. Okay, now we're on to the easy bit. The derivative is defined by the r prime of t is equal to x prime of t, y prime of t, z prime of t. Simple. All three functions have to be differentiable at t, and that's it. That's all you need to know. Find the derivatives of these functions, and I will see you in a couple seconds. Okay, you should have already finished finding the derivatives. If not, then you should pause the video. So let's go. S prime of t is, you can do 3t to the negative second power, but I will just calculate it in my head. S prime of t is negative 6 over t to the third power. If you don't see that's a 2, then I'm sorry, but I didn't prepare the video well enough, I guess. Sine of 2t is the chain rule, so that's 2 cosine of 2t. The 1 is gone. And square root of 1 plus t squared is also the chain rule. It is t over the square root of 1 plus t squared. Natural log of 2t is 1 over natural log of 2t. Or no, I'm sorry. It's not 1 over natural log of 2t. It's 1 over t. But first of all, L prime of t. Our cosine of t is negative 1 over the square root of 1 minus t squared. And t plus 1 over 3t to the 1/2 is 1/3 times 1 over 2 square root of t, right? And this is 1 over 3 to the 1 over t to the 1/2, so that's t to the negative 1/2, so you'll get negative 1/2 t to the negative 3/2. So this actually becomes minus t to the negative 3 over 2. And that's the exercise. Now I would like you to show something. I would like to show you something that might be a little bit useful later on, when we derive proofs of other things that we have that we are going to use in this vector function unit. And it's that if the function r of t, r of t, remember the bold means function, vector function, r of t, the absolute value of it or the magnitude of it is constant, then r of t and r prime of t are orthogonal, right? So we know that, actually you guys should try this first. It's actually not a very easy question, but if you can do it, then put in the comments. I'll pin your comment. Actually, you guys can just look ahead. Never mind, I won't pin your comment. Okay, anyways, if you can find another way to do it, I'll pin your comment. So show that if this is constant, then this is orthogonal. So we know that r dot r, right? R dot r, this is the textbook way, is equal to r squared. Yeah, and I'm not gonna lie, I looked from the textbook to find this way, right? The absolute value of r squared, or the magnitude of r squared, which is equal to, let's say if this was equal to c, right? If r of t was equal to c, then this would be c squared. Okay, so since this is c squared, what we can do is we can just remove the intermediary step. We can do this equals c squared. Now differentiate with respect to whatever variable you want. I'm going to differentiate with respect to t. So what you'll end up getting is r prime dot r plus r dot r prime, that's the product rule, right? The product rule still applies, is equal to 0 because the derivative constant is 0. So what you end up getting is 2r dot r prime. This is commutative, so you can change r prime dot r, and you can change r and r prime. So I'm actually going to put a very, very big disclaimer after this. So this is equal to 0, so that means r dot r prime is equal to 0. And this is the definition of perpendicularity for vector function for vectors in general. So therefore r and r prime are orthogonal, right? That's the proof. So note, so this step, right? Note, I'm gonna put a note, r cross r prime, or no, not this step, I'm sorry, the step above it. So note, d of dt of r cross r prime is not commutative, has to be this order. Has to be this order. This is equal to r, or no, I'm sorry. Well, actually, I'm just gonna say a and b prime, because r and r prime is really kind of ambiguous. So a and b. So a cross b is a prime cross b plus a cross b prime. Exactly this order, or no, b prime. It has to be this order. It cannot be b cross a prime plus a cross b prime, because you know if you switch the order of the cross product, then what you end up getting is blasphemy. What you end up getting is the negative. You can do a cross b prime plus a prime cross b, but that's going to cause issues when you go to the quotient rule. So we don't want, right? We don't want that. So a cross b plus a prime cross b plus a cross b prime has to be exactly in this order. It cannot be in like if you learned it as f prime g plus g prime f, then that you're in trouble. If you learned it as f prime g plus f g prime, then that is the correct order. So it's basically f prime g cross f g prime. Or no, I'm sorry, f prime cross g plus f g prime, or f cross g prime, basically like that. But in the regular single variable product rule, you will probably see it like this: f prime g plus f g prime, right? Integrals, exact same thing. Try to evaluate the integrals. Now, one thing that you have to take into account is the plus c is not just going to be an ordinary plus c. It's going to be a vector plus c, right? So it's going to be like a plus c with a vector on top, kind of like that. But otherwise, it's pretty similar. So try to evaluate your integrals, and I will come back in 3, 2, 1. Okay. So 36, very standard. From 1 to 0. So I'm not giving, well, yeah, sure, I'll simplify. So what I'll end up getting is this is equal to, well, this is j and k. They use j and k. I'm just gonna convert it into this form because I like it better. So this is, I'm guessing this is like in 3 variables because they're using k. So the integral of 0 is c, right, or c1. That's what I'm going to say. The integral of 4 over 1 minus t squared is 4 tan, or 4 times arctan of t, or plus c2. Well, actually, we don't really even need the c's because it's a definite integral. So we're just going to say nothing 4 arctan t, and then 2t over 1 plus t squared is natural log of 1 plus t squared. evaluated from 0 to 1. Oh, I'm sorry. Yeah, I need to cross those because I didn't want it to do all the questions, because that's gonna take a really long time, because you guys should already know how to do this. So what's arctan of 1? Arctan of 1 is exactly pi over 2. No, not pi over 2, I'm sorry. It's not pi over 2. It's pi over 4. So that means this is pi. And then this is natural log of 1 plus 1 is natural log of 2. Right? And then minus 0, still 0. Arctan of 0 is 0. So 0. And then ln, that's 0. So you'll just get 0 pi natural log of 2. That is your integral. 3 sine squared t cosine I hat plus 3 sine t cosine squared t j hat. A little bit crazy, but we can still try to solve it. So most important thing right here is basically reverse chain rule, or u sub. So you could set u equals sine t, and then cosine t will be equal to v, right? Yeah, I chopped off the question at that. So it's supposed to be 2k dt, right? Anyways, 0 to pi over 2 of these functions. So let's integrate the first function. You'll get u, so you'll get sine to the third power of t, right? And then this is, well, this is cosine this time, so u will be equal to cosine, so you'll get negative cosine to the third power of t, and it's 3, so it's very nice. And then 2, and then there's this k, so you'll get 2t. And this is evaluated from 0 to pi over 2. And then this is equal to sine to the third what's sine of pi over 2 is 1. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And then that's pi. Minus sine of 0, 0. Cosine of 0 is 1, but it's negative, so negative 1. And then 2 is 0. So this is equal to 1, 0 pi minus 0, negative 1. It's 1, 1 pi. And that is the answer to the question. Okay, I need to include the pi with the thing as well. Okay, this is just messy. I'm really sorry. There you go. Next question. This is a little bit hard if you don't remember your rules. If you don't remember your rules clearly, this is going to be a pretty hard question, but we'll try to do it anyways. So t e to the this episode is already 30 minutes long. T e to the 2t. How do you integrate that? So you integrate that by parts, or tabular, or VI method, or Wolfram alpha. It doesn't matter. But you have to know. You should know how to integrate this. You set u. You choose a u and a dv, right? So u is equal to you set u, let's say u is equal to t. What you want to pick u is, you want to pick u for functions that can disintegrate easily, right? You don't want to pick u for functions that don't do that, because what happens is you will end up integrating infinite amount of times, which was definitely not what we want to do. So du becomes 1, and then v becomes 1/2 e to the 2t plus c, but it doesn't matter because we're gonna get rid of that anyway. So uv 1/2 t minus, or 1/2 t e to the 2t minus v, the integral of v du, which is 1/2 e to the 2t. So the integral of 1/2 e to the 2t is 1/4 e to the 2t, and then plus c, right? Then now in this case we'd actually add a c1, because there's no, it's not a definite integral. T over 1 minus t is, we could actually rewrite that function so how we would rewrite it is as is t is 1 minus t is equal to t minus 1 plus 1 over 1 minus t, which is equal to t minus 1 over 1 minus t plus 1 over 1 minus t. This is easy to integrate. This is negative 1. That's just negative 1 because it's 1 minus t flipped. So if you do negative, you can flip the function. If you do negative, you can make it into negative t plus 1, which is the same thing as 1 minus t. So it's minus 1 plus 1 over 1 minus t. So to integrate this, that's just minus t, and then plus, or I'm sorry, minus, because it's the chain rule, natural log of 1 minus t plus c. c2. Next is 1 over 1 minus t squared. I don't know if you remember this, but it's just arcsine. Right, arcsine t plus t3, or c3. So what you get is, this is equal to 1 half t e to the 2t minus 1/4 e to the 2t minus t minus natural log of, well, you don't actually have to do the t1 t2 c1 c2 and c3. All you have to do is just acknowledge that and then add a plus c with a vector through it, or add a vector constant of integrations, but what it's called. So just add a plus c with a vector through it. That will work. So that's it. I'll see you guys next time for curvature, which is going to be a pretty interesting topic.